Okay guys, today we're doing 5.8. It's intermediate related rates. Today we're doing basically two types of problems. They're called the ladder problem and the shadow problem. And your worksheet will also go back and do some of those beginner related rates as well. So let's just get started. I'll show you how to do these two problems and that'll be today's lesson. Okay, first thing, let's just remind ourselves of the steps. The first one was draw a picture and label any givens, yeah? And figure out what it is that you don't know, yeah? After you do that, you need to figure out the formula it is that you need. Then you're going to plug in any non-changing variables if this is even a step that's needed, okay? In this case, for the ladder problem, it always is a step, okay? So you'll see that step today. After you figure out you plug in any non-changing variables, you take the derivative of the formula you have and solve for whatever it is that you're solving for. Let's get started. I'm going to start us out on the ladder problem, okay? So let me get a pen out. Okay, it says a 13-foot ladder leans against a vertical wall. Okay, so we have a wall, not very vertical, but there's my wall, there's my floor, and we have a ladder leaning against it, okay? And here I'll kind of give it like ladder features. Give it some steps on there. Okay, and it's a 13-foot ladder, so let's put that right there. 13-foot ladder leans against the vertical wall. If the lower end of the ladder is pulled away from the wall at a rate of 2 feet per second, okay, so that means that somebody is pulling this away from the wall at 2 feet per second. Okay, someone's pulling the ladder away. So if you're pulling this away, obviously this is going to fall down, right? So let's see this. How fast is the top of the ladder coming down the wall? So we're looking at how fast this is changing. So here I'll put a little question mark next to it. We're looking at how fast that is changing, going down the wall. At the instant the top is 12 feet above the ground. So this distance right here is 12 feet. Okay, so if you look at everything that we have, because we've now finished step one, we've drawn a picture and we've labeled everything we have. Now let's go on to step two and figure out what formula is it that we're going to be needing to use here. Now if you notice from the beginning related rates, it looks very similar to one of the problems I gave you yesterday. You have a right triangle and you have two sides of it changing, right? So that means that we're going to be using Pythagorean theorem on this one, okay? So there's my formula I'm going to use, and I know I'm going to eventually need this length, so if we want to solve for it already, we can, using Pythagorean theorem, or I can just wait till I plug stuff in and I can see what it is I'm missing, okay? And I'll just take that route. I will just wait till the end when I see everything I need. Okay, so next thing I need to do is step 3, because I did step 1, drawing and labeling. Step 2, I found my formula. Step 3 is plugging in any non-changing variables. Okay, so this side is changing, the ladder's falling down. This side is changing, it's being pulled out. But if you notice, the length of the ladder is not changing. The length of the ladder will always be the same. So this C value doesn't change, so I can plug that value in. So instead of C, I'm going to put 13 squared. And this is going to be some number, right? So let's just go about, I plugged in my unchanging variables. And so that's step 3. Step 4 is take the derivative of it. Okay, so let's take the derivative. The derivative of this is going to be 2a dA over dt plus 2b dB over dt. We did this yesterday, right? Equals, now the derivative of this, remember this is just 169, right? 13 squared is 169. The derivative of a number is 0. So we can just do that. Now, real quick, before I finish this off, I want to show you what you would have done if you wouldn't have plugged in an unchanging variable, okay? you would have left it as a squared plus b squared equals c squared. So this is the side that if I would not have plugged in my unchanging variables, I would have had 2a dA over dt. Now it's going to give me the same answer, okay? I want you to know that it will give me the same answer. I just want you to see how. Okay. So now we're at step 4, right? We took the derivative, okay? This is using the plugging it in. This is not plugging in. So not doing step 3 right here, okay? So I'm basically doing this 2 different routes. Okay, so step 4 is I did the derivative. Step 5 is solving for whatever it is we're solving for, right? We're looking at how fast this is changing. Okay, I can call this my A, so this is going to be my dA over dt. This will be my B, so this is going to be my dB over dt. So I'm looking for the change in B with respect to time. And this will be my C. And how fast is my C changing? My dC over dt is 0. Okay, I don't even need to know any of that if you plugged in non-changing variables. If you didn't plug in non-changing variables, like over here, then you do need to know all that. Okay, so let's plug in everything we know. So 2 times A, I don't know A. So I would have to use my Pythagorean theorem to figure out A, right? And I can't write right there. I'm going to have to do it over here. 12 squared plus A squared equals 13 squared, right? So that's going to be 144 plus A squared equals 169. Okay. Now I'm going to subtract the 144 over, so 169 minus 144 is going to be 25. So we're going to have A squared equals 25, and square root, so A is equal to 5. So this length right here is 5. Okay, and also you can get rid of those 2's if you want to, because you can divide by them onto the other side, just like I showed you guys yesterday. So we're just going to have A is 5, dA over dt is 2, plus, my 2's gone, okay, B is 12. The change in B is what I'm looking for, so I will just leave it as dB over dt equals 0. Okay, that's going to be 10 plus 12 dB over dt equals 0. And that's going to be, I can subtract this over, so it's going to be 12 dB over dt equals negative 10. Okay, so my answer is the change in B with respect to time is going to be negative 10 over 12. Or that could also be simplified as negative 5 over 6. And my units, B is measured in feet, and my time is measured in seconds. Okay, that's my answer right there. It's falling down, that's why it's negative, okay? Now, let's say you did not plug in 13 for the unchanging variable and you ended up here. Okay, notice what's going to happen here. You can get rid of the 2's just like I showed you on the last lesson. So it's going to be dA over dt plus B dB over dt equals C dC over dt. Oh, sorry, dC over dt. Okay, now A you have, it's going to be 5. You're going to plug in 2 for the change in A plus B is 12. Okay, plug in 12. And we're looking for dB over dt equals, okay, C is 13, and the change in C, since C is not changing, would be 0, canceling out this side, leaving you with a 0 over here. And if you notice, that's the exact same thing as you got. All this right here is the same as right here. So solving for it from that point would then yield negative 5 over 6. So if you don't plug in not changing variables, it's not a big deal, but you're going to have to notice that the thing where it's not changing, like the change in C over change in T, is 0. Okay? You're just going to have to notice that. It's going to have to be something that you see and you realize that that's happening. Okay, so let's do, that's the ladder problem. I believe they ask this more often than the shadow problem. So I think you need to focus on these. I have them on the worksheet, so make sure to do them. And let me show you the shadow problem now. Okay, the shadow problem is another problem they like to ask on the test. So this one is probably the ones that people find pretty difficult to solve. They just forget steps on this one. Okay, it's not as easy to see things on this one as it is on the ladder problem and other ones. A man is 6 feet tall and walks away from a 22-foot tall post at some constant rate. Okay, so I got some post. It's actually supposed to be a light post, okay? So, oh, I did write light post. So it's emitting light, and we have some guy that is walking away from it, and he is 6 feet tall, and the post is 22 feet tall. Okay, and they are a certain distance away from each other, right? If his shadow length is changing at 3 feet per second, okay, so he has a shadow he is emitting on the floor as well, right? This right here, that's the shadow. And I'll call it S for shadow. Okay, and then I'll call this X for the distance from the pole. Okay, and then if you notice, this light being emitted, it's going to hit the top of his head and it's going to create that shadow that we have here. So that's what's creating the shadow here. So if you notice, we got some triangles going on here. Okay, and I didn't label everything yet. I did label the heights, but I also need to say that if the shadow length is changing at 3 feet per second, so the change in the shadow length is 3 feet per second. And we don't actually know the shadow length right now, so I'm just going to leave S as S. At what rate is the man walking? Okay, so we're looking for how fast he's walking. Notice the speed of his walking is going to be dependent upon how fast the change in this is. This will be his walking rate. Okay, and that's probably what people find the most difficult to notice. This is the speed of his walking. Okay, it's going to be the rate of change of the distance between him and the post. So depending on how fast him and the post are changing distance, that would be how fast he is walking. So that's what we're going to be looking for, because it says what is the rate the man is walking. So we're looking for dx over dt as I've done this. Now, that's all step one. We drew it, we labeled things. Step two would be finding the formula we're going to be using, which this is what a lot of people find problems with as well, is figuring out what formula it is we're going to be using. Well, what we have here is we have two similar triangles. We got that triangle, and we got the larger triangle. Yeah, the big one. And they're similar. So that means that the height over base of both the triangles are ratios of each other, right? So let's do that. The height, say 22 over the base, which the base of it is x plus s, the distance from the man to the post and the shadow length, is equal to the height of the man over the shadow length. Okay, so that's my similar triangles right there. You got your big triangle and you got your small triangle. Okay, now step 3 is to plug in any not changing variables. Well, both x and s are both changing, so we can skip step 3. Step 4 is going about and taking the derivative, right? Okay, well, this is going to be quotient rule and everything. I don't really want to deal with quotient rule. I can manipulate the problem before I take the derivative here. And if you see, this is why there's a lot of people that find these shadow problems pretty difficult, is first of all, they don't understand that this means how fast he's walking. Okay, that's the distance between the post and the man's changing, is how fast he's walking. Second, they don't realize it's a similar triangle that they can set up the formula for. Third, they don't notice that you need to manipulate it before you take the derivative, or your life is going to be difficult. So in order to manipulate it, let's cross multiply. 6x plus s equals 22 times s. Yeah? That's just cross multiplication right there. Now I'm going to distribute this 6. So we got 6x plus 6s equals 22s. I can subtract the 6 over, so it's going to be 6x equals, we got, what is that going to be, 16? 16s, yeah? And then now, this is the easiest way to manipulate it, and now it's easier to take the derivative. Okay, so now I can do step 4, I can take the derivative. And the derivative would be 6 dx over dt. That's the rate at which he's walking, which is what we're solving for. And 16, the rate at which the shadow is changing, which we know is 3. Okay, so let's just plug in our stuff and solve. So we got 6 dx over dt equals 16, the change in the shadow, which is 3. Okay, now let's move this up here. And we can divide by that 6, right? So we can say that the walking rate is equal to 16 times 3 divided by 6. And let's simplify this. Instead of doing 16 times 3, I can just do the 3 divided by 6. I can say that's going to be 2 on bottom, and 16 divided by 2 is 8. Okay, so it's going to be 8, and x is measured in feet, and the time is measured in seconds, I believe. Yeah, seconds. So that's how fast the man is walking. 8 feet per second. Okay, now they could also ask a question like, how fast is the rate at which the post to the tip of the shadow is changing? If it asked something like that, you would just add the 2. 8 plus 3 would be 11 feet per second. That's how fast it's changing at the time at which we're talking about. But that's how you do this, and people find the shadow problem difficult just because it's a little different than some of the other ones that we've done. It follows the same steps, but it takes the steps and tweaks them a bit, okay? So like this one, it's kind of hard to see that that's a walking speed. It's kind of hard to see that these are going to be similar triangles that you're going to have to set up. It's kind of difficult to notice that you should cross multiply in order to simplify it before you take the derivative. Just these are things that you need to notice in order to make this problem easy. That's it.